So welcome to lecture number 10. So first, I will go through the school learning again, and then in the second part of this lecture, I will talk about unsupervised learning and the so-called k-means clustering algorithm, which you should implement in homework number 3. So recall that after doing a lot of examples here in the supervised learning world, we started last time talking about reinforced learning. And we had this example with this car, but also we had this example with the campus and the lecture hall in Combini. And I will mention this again today, and then later talk a little bit about this. And then in the second part, we go here to the clustering, which is part of unsupervised learning. So what was this basic idea for this reinforcement learning? So in comparison to supervised learning, so in the case of supervised learning, we had some trainings data where we always had a feature and a label. So we had some supervisor who told the program what these things are. So it gave an example of a picture of a dog, and it said, this is a dog, and so on. And in the reinforcement world, there's no supervisor, but there's just a program who tries and to interact with the environment, and then it gets a reward from the environment and new states. So we have this program here, or the machine or the robot, which we call the agent, and this agent can do some action, and then the environment, whatever this means, will give back some reward and also a new state. Yeah. So in the chess example, the agent is maybe the chess program. Then an action is to move a chess piece. Then the environment is the other chess player who will also receive your move and then will react to your move and will give back a new state, meaning a new chessboard where he also put a piece. And at this point, when he's playing, you don't get a reward, but at some point you maybe make the final winning move, and then you get a reward by winning. Or the environment, meaning the opponent, makes the final move, and then you get a negative reward by losing the game. And this general setup is usually described by this Markov decision process, which was a thing of 4 things. So we had a set S, a set A. So we had the set S, the set of states. Then we had the set A, which was a set of action. And then T and R were 2 maps. So this T was this transition probability function, which told us the probability that if we are in some state S and then take some action A, that we will land in some state S. The value of this function at these 3 points tells us the probability that going from one state to the other state by using the action A. But in a lot of examples, if we are in some certain state and we do a certain action, then often there's actually just one possible state. For example, in our lecture hall Combini example, and if we move in one direction, then I'm starting in one state and going up, there's just one possible state we can land in. So in this case, these probabilities are always, almost always 0, except for always one state. Yeah, and then R is the reward function, which tells us what do we get when we go from one state to the other state by using a certain action. And this will be a real number, which by a positive real number usually means some positive reward, and a negative number means some negative reward. And so then we had this example here with this robot car, which wants to travel far and quickly. And there were 3 different states. So the set S was a set of 3 elements, namely the elements were cool, warm, and overheated. And there were 2 different actions this car can do. It can slow down or it can speed up. And then we see here in this picture these transition probabilities. So for example, here, going from the state cool to the state warm, using the action going faster, the probability is 50%, or staying in the same state is also 50%. And going faster gives a reward of 2, and going slow gives a reward of 1. But here, if we are already in the state warm and we go fast, then our car overheats and we get a reward of -10. Yeah? Okay. And so how do these dynamics of such a system usually look like? So usually we will start in some state S0. So for example, we start in the state cold, and then we choose an action, for example, going faster, and then we get a new state, which is maybe, again, we are still cool, or we go to the warm state with a certain probability. And maybe what was confusing last time, that here I talk about an explicit example of going from one state to another. So here I will start with, so this is, let's say, one episode of a program. So I start in one explicit state, then choose an action and get one explicit state back. So it's not that at this point here I consider all possible states at the same time. So this here really describes one explicit way. Yeah. And going to the state from S0 to S1 gives us a number, a reward, going from S0 to S1 using action A0. And this we do again and again. We choose an action and so on and get a reward back. And what we in the end get as a reward is the sum of all of these rewards on our way through the program. And so this is the so-called total reward. And we also have this, this discount factor, which can be interpreted as a factor which somehow makes the early rewards more important. So if this number, gamma here is 1, then I just have the sum of all rewards I get at each step. But if the gamma is smaller than 1, then the later rewards, which take some time until I get them, they are less important. And of course, the goal is to choose an action here such that we can increase this total reward. Yeah. And and choosing actions is what we call a policy. So if we are in a certain state, for example, we are cool or warm, then a policy tells us what we should do in this certain state. So a policy is a function from the possible states to the possible actions. And then the goal of our program is to find the optimal policy, which will increase our total reward. And here was maybe the first confusing formula, which is now the value of a policy pi. So the statement is that this is a function on the space, on the set S. So I can get the value for each state. And the value of a policy at a state S is this here. And what this means is that we take the expected value, because now we consider all possible cases. So if we are in a certain state, then doing an action can lead to different states with certain probabilities. So what I want to consider here is the expected value, considering all possible ways of going from one state to the next. So that's why we need to choose the expected value here. Yeah, and what this here means is that we consider this total or this discounted total reward by starting in the state S, and we take the expected value. Because starting in S0, the S1 can have different values. So with certain probabilities, S1 could be either this state, or this state. And what we want is to consider all these possible rewards we can get going in all these different states. And we want to get the expected value of this by choosing the action using this policy here. So if we are in a certain state Sj, then the action we choose is determined by our policy. Yeah. But for example, in our Combini lecture example, we actually don't need the expected value here, because in this case, it's clear if I start in one state and choose an action, then there's just one possible state. So there's actually really just the sum of these things here, and we don't need to take the expected value. And what this number here really just means is this interpretation here, namely that if I fix a policy, a way of deciding, then the value of this policy at some state S is the expected total reward I can get by starting in this state, choosing this policy. Yeah? So are there questions on this notion? Okay. And then we introduce what we called an optimal policy. So an optimal policy we denote by pi star. And this is defined to be the policy which maximizes this value. So meaning that this has this property here, that this value of this optimal policy at any state, so the expected total reward I can expect by starting in state S is given by the maximum of all possible values over all possible policies. Yeah, and in this car example, it is quite clear what the optimal policy was, because of course we want to go, we always want to go fast, but of course if we are warm, we don't want to go fast, because with 100% we have a reward of -10. So therefore, clearly the optimal policy of warm should always be slow. But of course, if we are in cool state and we want to maximize our value, then we always want to go fast, because we get these 2 rewards instead of going slow. So therefore, the value or the image of the state cool of the optimal policy here is fast. Yeah, so in this example, it's quite clear what the optimal policy looks like. Okay, and of course the goal is to find the optimal policy, but of course it's quite hard to find it by considering all possible policies. So we first rephrase this a little bit by using this so-called state action value function. And I will try to make this really explicit in our Combini example. And I hope then this becomes clear. So what this function here is, this we denote it by Q star. So this function here, Q star, is a map from S times A to R. So for each state and each action, this gives a number. And this number tells us the expected total reward we get when we are in state S and we choose action A. So this here, this Q star SA, we So we are in state S and we take action A, using the optimal policy. And so if we are in some state S and choose action A, then the reward we get at the immediate step is this one here. We are in state S, we take action A, and we go to state S prime. And the probability of going to S prime is given by this transition probability function here. Yeah. So therefore, this here gives us exactly the expected value of the immediate reward, because we take the probabilities of landing in some state S prime and multiply it with the reward we get when we land in the state S prime. So this is the expected value for the immediate reward. And then afterwards, we want to know what are the next rewards. And therefore, what we do is we take this sum here. So again, we take the probability of landing in state S prime, and then from S prime, the expected total reward is exactly this function here, because the value of the optimal policy of S prime is exactly what we can expect as a total reward when starting in S prime. Yeah. I don't know, is this function maybe clearer? I hope at least it will be when we do it in our example. But the main point here is, assuming we know this function here, then we can also get back the optimal policy, because the optimal policy then, if I want to know what should I do when I'm in state S, well, I just need to check what is the largest value of this state action value function when starting in S. So for which action does this value here give me the biggest expected reward? And then the corresponding action, which gives me the highest value here, should be then the value of this optimal policy. Yeah? Okay, so now let's do an explicit examples with numbers and try to understand this function Q. So we had this example here, this silly example of combini lecture. So the setup is that we are on the campus, and there are different positions where we can be. And so the different states are the positions on the campus. So in this case, there are 56 positions. And there are also some special states, namely the green parts are combinis and the red parts are lecture halls. And there are 4 possible actions going right, up, left, and down. And the reward we get by entering a green cell is +1, because we want to go to a combini. But entering a red cell gives us -1. And making just one step to an empty cell is -1. Yeah, because just walking makes us tired. And what we want is to find the starting somewhere. We want to find the shortest way to the next combini. And so, for example, here we had this example of an optimal policy. So here we can see in each state what the optimal policy is. So if this here is state S, then the statement here is that pi star of this S, in this case, is the action going left, right? Because the policy is a function from S to A, and A is a set of these 4 directions. But now let's make really clear what we mean by this state action value function. So let's take a smaller example. So let's say we just have these 4 states, and one of them is a combini. And now, so in this case, maybe let's give them name S prime, S2 prime, oops, and S3 prime. So we have 4 states, and we still have the same actions. So we can go in all directions. Or let's just say A is up, left, down, right. Yeah. And this state action value function now gives us for each state here and each action, so here at each point, this gives us a value. Yeah. So here we have the value Q star S, let's say, going up. And what is the value in this case? Well, we want to know, I mean, you can use this formula here. So, so what is the expected maximal reward we can get by starting here and going in this direction? Well, the best way to go to a combini is to go in the next step there, right? So therefore, in this case, so maybe let's first do this term here. What is the immediate reward by going this step here? Well, in this case, we go to an empty cell. So the immediate reward is just -1. So this here is, the value of this is minus 0.1, sorry, because we have this making a step to an empty cell is minus 0.1 plus, and then we have this term here. And now we need to look, when we are in this state here, we need to find the maximal. So first of all, there's just one summand here, because going from there to there, we will just end in one state. And now from here, we want to know what is the maximal expected reward. And this one is, when we go in this direction here, we would get +1. Yeah, because going here, well, I should say that in this case, we maybe just say, if we go in this direction, we go back on the same. So this here would give minus 0.1 and minus 0.1. But going this step here would give us +1. So therefore, in this case, this here, maybe let's write this explicitly. So this S prime is really this S prime here. The maximal expected reward we get is 1, because we can go there by using the optimal policy going left. So this here is 1. And that's why in this case here, we add 1. Yeah. So in this case, this here is 0.9. So somehow here we have the, maybe let's make this the color. So here we have 0.9 as the value of our state action value function for this state going in this direction. Yeah. And with the same argument, because this is sum of symmetric, we also have 0.9 going to the left. But for this state going to the right, which in this example goes back to this state here, we lose 0.1 because going to an empty cell gives us an immediate reward of 0.1. So here, this Q star of S going to the right is the immediate reward of 0.1. minus 0.1 plus, but then from there we know so we know that the value, the value of the optimal policy of S is 0.9. Yeah. So therefore here we have 0.9. So therefore this is 0.8. So here the value of the state action value function is 0.8. And with the same argument, we also have 0.8 here. Yeah. So maybe then I can write down the values at each place here. So here the value of the state action value function is 1, because in this state, going this action gives us the maximal value 1, because here we are in the final combini. Here it's 0.9, because we would go there and then there. So if we go in this direction, the best way afterwards, if we go here and then we go back, the best way is to go there. So we get minus 0.1 and then go there. So the same we also have here. And if we are in this state and go in this direction, we lose 0.1. And then from there, the best way is again there. So this here is 0.8. And so now let's fill out again the rest here. 0.9. And here we are just in the final state. Okay. So these are orange numbers are the values of the state action value function. Yeah. And this is what we want to get in the end. I mean, now we calculated them because we know the optimal policy, but what we want to learn in the Q learning algorithm are these numbers here, because these are exactly the value of this function. If we know these numbers, then at each point we know where we should go, because if we are in some state, we just look in all directions and look where's the largest number, and in this direction we go. So if we are here, then we see, oh, well, here we have 0.9 and 0.9. So in this case, it's the same. So for example, we could go here. And if we are here, we see the largest number is there. So we could go here. And then we end up there. Yeah, so this is what I mean by this formula here. If we know the values, then we can get the optimal policy in a certain state S by looking at all possible actions in this state and look where we have the largest value of this state action value function. So therefore, the goal is to find these orange numbers. And this is what we want to do in this Q learning algorithm, because we want to learn these values of Q. And what we will do is we start with some random numbers or zero numbers, so that we will start with zeros everywhere. And then we will use this algorithm and this Bellman equation to slowly get an approximation for these orange numbers. Yeah. So let's recall this algorithm, and then we will do this algorithm step by step again in this one example. And then I hope it will become clear that we will approach slowly these orange numbers by using this equation here. So the goal is to find an approximation for these Q star values, so these orange numbers. And to do so, we try to learn this function Q here, which gives a good approximation for this. And we start with some random values. For example, we set everything to be 0. And then we start at some state. And then we look at all possible actions we can take at this state and go in the direction, or we choose the action with the currently highest Q value. Where at the beginning, maybe all of them are 0, so maybe we just choose one of them. Or what we also do by a certain percentage is sometimes we just choose a random action. Yeah, this is this so-called epsilon greedy algorithm. But maybe this is not so important now. And if we do this, if we choose some action, then we will get a new state, and we also get a reward. And then what we do is we update this value where we went by choosing this formula here. And so first of all, we have again this so-called learning rate, which somehow tells us how fast do we change our mind. So we have some value in this Q. And now we want to update this. And what this factor alpha just tells us is how important this new information will be. So here we have this 1 minus alpha. We take the old value plus alpha and then the new value. So if alpha is 1, then we forget completely what was the current value, and we just take this number here. And if alpha is 0, then we don't change anything at all. Yeah, and maybe the tricky part is to understand this thing here, but this we will see in a second. So we do this, and then we land at some state. And if this is not the terminal state, then we will go back to number 3 and do it again and again until we are at some terminal state. Okay, so let's do this. So now let's try to understand this formula here. So why is this update using this so-called Bellman equation leads us slowly to these orange numbers we want. So in the first episode, so by episode, I mean doing a complete run and ending at some terminal state. This will be one episode. So in the first episode, let's assume we started everywhere by putting everywhere 0. Yeah. These are the values Q. So these are our values Q at these different S prime, S2 prime, S3 prime. And here maybe also zeros. And now we choose some S0. So let's say this here is S0. Let's say S0. And well, we start with some S0. And now we look at the current best actions in this state, where at this point we look at these 4 numbers here, where in this case we see all of them are the same. So we choose maybe just this action here. Yeah. So let's say A0. Okay, so S0 is S and A0 is up. This here is A0. So what is the reward we get? Well, in this case, the reward we get is minus 0.1. So R0 is minus 0.1. Yeah. So if we do this step, then this formula tells us we should update this value here. So this here is Q S0 A0, which is 0 now. And the new value is, well, we take 1 minus alpha times the old value, 0, plus alpha times this value here. And in this case, okay, let's write this out. It's 0 plus alpha and R0 is minus 0.1 plus, and maybe now let's take the example where this discount is just 1, so we don't discount at all. And now what we want to do is, in the new state, we want to see, want to find the maximum of all these values. But in this case, the maximum is 0. So in this case, we have 0. Yeah. So in this case, and maybe also choose an alpha. Maybe not. I think it will become clear. So in this case, we just have alpha times minus 0.1. So this value here will get changed to alpha times minus 0.1. Yeah, so we can already put here for the next, or maybe not. So we get the new value here. And now we are in this state here. And so S1 in this case is S prime. And again, so we are now again in step 3. So at the current state, we again try to find the maximum value, but still here everything is 0. But let's be lucky and maybe say A1 is this one here. Yeah, so we go in this direction here. And then the reward R1 in this case is 1. So the new value here, the QS, let's say S prime. So here, this is a new value of QS up. And what we get now is the new value for QS prime going left. This is the old value times 1 minus alpha, which is 0, plus alpha times the immediate reward, which is 1, plus, and in this case here, again, the maximum value of these, which is 0. So 0. And this gives then in the end just alpha. Yeah? Alpha. But now we are in a terminal state, so this episode is over. And the result of this episode is that now our Q has the following values. We have here, we didn't change anything. But here we have minus 0.1 alpha. And here we have 1.1 times alpha. Yeah. So now we do the same game and start, maybe let's also start here. And then we look in all directions and see for the maximum. Well, in this case, we wouldn't go in this direction because this here is smaller than the others. So maybe we would go in this direction, but maybe would see that we get a minus 0.1 alpha here. And then maybe go in this direction. Maybe at one point, after a few steps, all of these values will be minus 0.1 alpha. But we know the true value we want to have later is we go here, minus 0.1 in this direction, and then going 1 point here. Yeah, so for example, maybe let's make it clearer with the case alpha equals 1. Then here we have this and 1. Then we already see that these two values are actually the correct values for Q. So if you recall, so I mean, this value is the correct value for Q, but here we now have minus 0. Alpha. So maybe this we can do. So if we would go in this direction and then this direction, then the updated value here would be, well, the old value or this reward plus, and then the maximum at this case here. So at this point, we would add this 1 to the value here and would get something the value here will be this plus some gamma times this factor here. So therefore, this value will be become closer to the actual value. Yeah, I don't know if this now became clearer that this here somehow looks at the new state and then looks in all direction and decides which has the highest value. And also this gamma here, because it's one step ahead. So this gets a factor gamma. And then if from there to there, this also gets a factor gamma. This would mean that going from there 2 steps, we would get a factor gamma squared. And this is also what we include in this discounted reward. Yeah. Okay. I don't know if this helped or not. I hope. Are there any questions on this? So maybe you should play around with this notebook I gave you and maybe make the example smaller. And then maybe for each episode, look explicitly at these values, or maybe even try to draw these values in the diagram instead of just these arrows. And then maybe you will see this picture here that these numbers, if you do this again and again, will slowly converge to these correct orange values we want. Okay. And yeah, so my original idea for homework 3 was to implement this Q-learning for this game, tic-tac-toe. I don't know how you call this here. Maybe not like tic-tac-toe, but I think the game is clear that it's a game for 2 players where one player makes an X and the other makes a circle. And the goal is to get get a diagonal or horizontal or a vertical line. And this you can also implement by using this Q-learning. And the really nice thing here is that you don't need to be smart to implement. I mean, of course, it's clear somehow. If you think about the game, there's an easy strategy to always win or to get a draw. So you can also compute it directly. But the nice thing about this Q-learning or this reinforcement learning is that you really just let the program try and error, and it will figure out the best strategy by itself without telling it. Of course, in these simple examples, it's faster to just implement the correct, the perfect strategy. And also one should say that Q-learning is maybe not the best strategy for tic-tac-toe. So one reason is because it's quite a big state space. Because what is a state here? A state is a possible board situation. So for each entry here, so we have 9 entries, there are 3 possible states. It could be empty, X, or a circle. And therefore, it's 3 to the 9 states. Well, it's less than this because not everything could be an X, but it's roughly 3 to the 9 states. And so usually you would not use this naive approach of this Q-learning to attack this problem, but maybe it's a nice thing for the more advanced people to try to implement this. But instead, I will present an easier homework 3 for you. But maybe if some of you implement this, maybe you can share it with the others. Okay. So let's go now to the second part of the lecture, namely, we're going over here to unsupervised learning and this clustering. So, and what is unsupervised learning? Well, it's like supervised learning, but without a supervisor, meaning we just get some data of something, and then our program or the machine should try to see some structure in this data. Yeah, and this can be used in a lot of different things. So, for example, here in signal separation. So, if you have, for example, an audio recording of 3 instruments, then it's the sound wave is the sum of all these 3 different sound waves. And there are programs who can somehow figure out that in this sound wave there are somehow 3 sources for this, and then there's a way of separating these 3 sources. And yeah, also in the anomaly detection. So for example, here you see a graph of the energy consumption over time. So maybe here it's day and night, and you see that you usually have this graph, but then there's a peak. So there's something strange there. And this would also be an example of unsupervised learning to write an algorithm who can see that this is not normal. Yeah, and there's no supervising, so there's no feature label here. It's just a set of data points, but somehow we can see that this is not normal here. And what we will do today is to see if we have data points like this, then maybe we see here that it seems that there are different so-called clusters of data points here. So whatever this data is, we see that here somehow a cloud, there's a cloud, and here. And the idea is to somehow find a coloring or a clustering of these data points. And the output of our algorithm will be something like this. So the input will be just numbers in R2, a collection of points in R2, and the output will be a function which assigns to each of these points a group or a color in this case here. And this is called a clustering. Okay. So, and so more precisely, what we will have is we will have a subset in RD. Well, in this picture here in the homework, the D will be 2. And we have some integer k, which we will choose. And then later we can discuss, we will discuss how to choose this k. But first we will choose. So we will try to find k different clusters. So here in the picture, k is 4. And the idea is to partition this set P into 4 different subsets in these so-called 4 clusters. So let's make this even more precise. So what we want to find is a map, which I call small c, from this set here into the set of the numbers 1 to k. Yeah, so here these k is 4, and these numbers just correspond to different numbers, to different colors. And what this map does is each point here gets mapped to a color. And then what we define is we define the cluster Ci, where I goes from 1 to k, to be all points in the corresponding cluster. So in this picture here, we have k equals 4. And maybe here this is C1, C2, C3, and C4. Yeah. And then, yeah. And yeah, so we see that this here is a partition of the set P. So P is a union, disjoint union of these Ci. And what we want to do is, well, we want to do it like in this picture here. So we somehow want that points in the same cluster are together. So this point here should not be in this cluster here. And how can we decide if points are together? Well, what we define is first, for each of these clusters, we can define its mean. So the mean just means somehow the middle point of all these points. So what we do is for each of these clusters, we take the sum over all points in this cluster, and then we divide by the number of points in this cluster. And in the picture here, this just means, for example, here maybe we have mu1. Here maybe in the middle we have mu3. Well, maybe red is not a good color here. Maybe here is mu2. And maybe here is mu4. Yeah. So this is by taking the average of all these positions. And then what we want to minimize. So we want to minimize somehow the distance of all these points to the mean of the corresponding cluster. And this is what this sum here does. So this is the so-called within cluster sum of squares. So within one cluster, we take the sum of squares. So we go through all clusters, and at each cluster, we sum up all the differences of these points to the corresponding mean, and take the sum of their, we take the norm, which is just a difference, and square it. Yeah, so that's why the sum of squares. And this is what we want to minimize. Because if this point here would be in cluster C4, then in the sum, this distance here would appear, and this would make this sum here big. So this, if we can minimize this here, this really then corresponds to this picture here, because here the teal points, they have the shortest distance to this one, and the red points to this one. Yeah, is this basic idea here clear? So we fix the K and we have the set P. And what this algorithm will do now is exactly try to find these clusters. Or more precisely, what we will find are these means. Okay, so this k-means clustering algorithm is called k-means because we are trying to find these means. So let P a set of n elements. So in this picture here, n is 200. So we have 200 points. And we fix some k. And what we want to construct are the means of our future clusters. And then if we have the means, so let's say here, again, mu1, mu2, mu3, and mu4. If we have these 4 points, then we can define the clusters by saying a point looks at all these means and then looks at the shortest distance, and whenever, and then it chooses the corresponding group. So for example, this point here is nearest to this one, therefore this will correspond to C1. So the statement is the Ci is a set of all points where the distance to mu I is smaller or equal to the distance between this point P and the other means. Yeah. So therefore, if we have these means, we can also define our clusters by just saying the clusters are the points which are closest to the mean. And then this algorithm is quite simple. So first, we start by choosing any means. So for example, we say mu1, mu2, mu3, mu4. And then we just do the following. So if we fix some means, 4 points, in this case here, then we can calculate the corresponding clusters. So for example, here, maybe this would get this cluster. Maybe this point here doesn't get a lot. Maybe this one gets here something and something like this. So we might have a really small see here for this mu, let's say C1, C2, C3, C4. So this will give clusters. And then we can recalculate the mean. So for example, here in this C1, we can, if we have this cluster, we can recalculate the mean by just taking the average overall and get maybe a new mean. And here we can calculate a new mean, and here a new mean, and here a new mean. And this will give new mu's. And then we start again at step number 2. Then we have new points, and for each point, we can collect the cluster. Then we can calculate a new mean and do it again and again. Yeah, so this is a really simple algorithm. And but at the beginning here, this initialize these values mu, there are also different ways to do this. So we will discuss 2 of them. So there are 2 popular ways to choose these starting values. So in the explanation before, I just choose random points in the plane. But there's a so-called Forgy method, which is named after some guy. And the idea here is to choose these means to be one of these data points. Yeah, so what we do is we choose of these, in this case, 200 points, we just choose 4 points randomly and then say these are our starting means. This is one way. So for example, here in this picture, maybe we choose this point here for the first mean, which gives this teal part here. And maybe we choose this one here to get this part here. And then we maybe also choose this one to get this part, and maybe this point to get this part here. So this gives these 4 clusters. And another way is to just put each of these points in a random cluster at the beginning. So we just choose this, this cluster function or this coloring randomly at the beginning. And then with this, I mean, with a really messed up cluster here, we can calculate for each of these numbers, we can calculate the mean. And this, if you see this picture here, this will lead to the fact that most of the means here will be quite in the center of this picture here. Yeah, so these are 2 different starting points for choosing these starting mu's. And then we just repeat this algorithm. And in this case here, so this is the picture. So in this case, I choose this test data here. Then here, this is what I get with this method. And this is what I get with this method. And in this case here, after doing this 20 times, in the end, I get this result here, which is what we maybe might expect in this example. Yeah, so both of them actually lead to the same result in this case. Okay, and the homework is to implement this here. So this here comes from my implementation, and but you can please feel free to implement it however you want. But for those who are not so sure how to implement this, I also created a template. So the homework 3, which I will share in a second, is to implement this algorithm, and then also try to think about the following questions, which you maybe have now in mind. Because I said we fix the k by ourselves, but maybe we want our program to decide what is the correct k. And but maybe you can try to figure out maybe how you can use this here to find the correct k. So the basic idea is to consider this this value here. I mean, I can do this algorithm for different k's, so I can start with k equals 1, do this algorithm, and in the end, I get a value for this within cluster sum of squares, which will give me a number. And then I can do this algorithm again with k equals 2, and I get another number. So the idea is that you can try for different k's, plot what you get for this within cluster sum of squares. And of course, if you increase k, if you allow to have more clusters, then this number becomes smaller and smaller. But you will see that in this case here, for example, where maybe the real answer is 4 clusters, that at this point, let's say 4, before 4, you will maybe really increase the value, but after 4, there's not really a big decrease. Oh, sorry, not increase, I mean decrease. After 4, we don't really make this value much lower than before. So if you plot these within cluster sum of squares with respect to the number of clusters, then the way to decide which is the nice k is a point where this curve is maybe not really going down much more. Yeah. And also, you should maybe play around with your implementation and see what is the difference between these two way of starting with the algorithm. And so first, what I give you here is a way to create some data, so you don't need to program 200 points by yourself. So there's a package, sklearn, which also includes some function, but there we can also have a function which creates us some data. So there's a function called make blobs, which is somehow it starts with creating clusters of a certain standard deviation. So it maybe becomes clear if I do just an example here. So let me run this code here. So in this case here, I choose number of clusters 4. The dimension is 2. And here the standard deviation is 1.5. So if I change this number and make it bigger, let's say 3, this just means that these clusters become wider. So if I run this again, oops, then you will see now, well, these are still 4 clusters, but it's more spread. And with this function, so the positions of the points are then here in this array points. And also we can actually get back the clusters this function used. So in this case, we can first just plot these points, but by using again this PLT, which we also used before. There's this scatter plot, which just plots these points, and then we can also use these clusters used by this function. So these were the 4 functions created by this. These were these 4 clusters created by this function. But this you can maybe just ignore at the beginning. So the point is that this function here just gives you some test data. And you can also increase here the number of clusters, let's say 8, and maybe decrease the standard deviation. And then we see here we have 8 clusters, which are a little bit tighter. Yes. So you have this data in this array points, and then here I just recall the content of the lecture today, or what I mean by cluster, and this within cluster sum of squares, and what we mean by a mean of a cluster CI. And then here is this algorithm I described. And the exercise is then to implement this algorithm. So what we want is we want to find this function which assigns to each of these points a number. And so again, you don't need to use this template here. You can implement it however you want. But how I did it is I said the clusters is just an array of numbers. So n here is the number of points we got before. And then in these clusters, which starts with 0, you will later maybe put in the corresponding cluster. So this will be a number between 0 and 3 in this case. And so this area means contains these mu1 up to mu k, and these clusters are the clusters. Yeah, so in the algorithm, you will update these clusters, and you will update the means. So what you want to change is always this area and this area here. Yeah, and then for these two ways of starting, you should implement this function, this forgy method and this random method. So this will, both of these functions should change this. Oh, there's a question. So the question is, if I start with the forgy method or the random partition method, if I always end up in the same result? And the answer is actually no. So if you play around with this, you will see that, I mean, in the one example I showed you, they both found the same clustering, but you will see that in general, you can end up with different results. So thank you for this question. But yeah, so one part of the homepage homework is then also to play around. So maybe I can show you one example here. So this is my finished implementation. So let's maybe let me create a new set. Okay. So let me do with a random. So here, even though k is 4, if we start with the random partition, then maybe how to say? So maybe one mean is outside here and the other means are inside. And then in the next step of deciding in which cluster they are, actually, we will just get the 3 clusters in the end. And if we use this forgy method with the same data set, then we actually see that well, the result here is not nice because I forced him to do 4 clusters. You see that the forgy method gives these 4 clusters in this example here. So I hope this answers your question, and you see that actually we get 2 different results here. So these are they started with the exactly same data set at the beginning. But maybe here, taking k equals 4, even though our example function, our create function used for, I think clearly here we just have 2 clusters. Yeah. But yeah, so for each of these steps, what I did is just implement these functions here, update these means. So this is just this function here, and also choose the clusters, which is just here. So if I have means, then I can assign for each point, I can assign in which cluster it should be. And where this function here, I just gave you the this within cluster sum of squares. So this just takes the sum over all differences between the points and the means. And then after you implemented these steps here, you can see here these k-means algorithm with the random partition. So here's just the initializing part is different. And here, this is just the drawing part. And this here is just the algorithm, which does step 2, step 3, and then it goes back and does it again and again. And the only difference here is step 1. And then the bonus exercise is to maybe try to decide which k is maybe the best for a given data set. So in this example here, maybe the answer to this should be k equals 2. So what I explained before, what you should do for this is then try to plot this WCSS compared with the k, and then see that after increasing the k, of course it will always go down because the optimal k is setting k equals n, putting each point in its own cluster, then the difference is always 0. But if you plot this, you will see that at some point it will not really get much better. So maybe somehow the derivative of this function, if it's smaller than a certain number, then at this point you should not increase the k anymore. Yeah, so maybe here you can find, maybe you can even make it automatically that your program decides the k. But one way to do this is just to plot it and then maybe decide by hand which is the best k. Okay. And yeah, I think that's all for the homework. So I hope this homework will come online in the coming hours, and then I will let you know, and then maybe you can discuss it in the study session tomorrow. But first I will stop sharing and then you can ask questions.